Hi folks, welcome to another episode of NYC CNC. I've had a lot of questions from folks on driving large stepper motors with Arduinos, so I wanted to do a quick video on it. What we've got here is a 24 volt power supply, a micro step driver off eBay, a Nema 34 stepper motor, and an Arduino. I'll go over the details later. And what I'm going to show you is two different ways in Arduino we can control this stepper. As a quick precursor to this video, I am not the expert on all the subject matter. I can tell you some basics, like for instance, Arduinos aren't actually the best processor to maximize some of this equipment due to I believe their processor speed. For instance, when you add in a serial command or other Arduino commands, you lose some speed control of the stepper. I'll mention that later. But bottom line, this is a pretty cheap, pretty quick way to do some pretty cool things with some pretty powerful motors. Let's talk hardware. This is a 24 volt power supply. Steppers need higher voltages. 24 volts will be fine for this application. You'll see a lot of CNC systems even run double or triple that voltage. This one happens to be 10 amps. It's the one I had laying around. If you've got a benchtop power supply or another source for 24 volts, just make sure it's got the amperage and you're good to go. This is a microstep M5045 stepper driver. There are many of these that are similar in their signal settings, so I would think most will be applicable. You can read the data sheet for various current ratings and microstepping toggles. This is a used Nema 34 stepper motor. This one happens to be rated at 5.5 amps, which is a little bit on the higher side. It is 640 ounce inches. I usually think in inch pounds, not ounce inches. To convert ounce inches into pound inches, you just divide by 16. So this motor is rated at 40 inch pounds, which means it can hold a 40 pound weight 1 inch out from the shaft, or it can hold a 1 pound weight 40 inches out from the shaft. So that's a pretty good amount of power. And finally, we've got a regular Arduino. This happens to be quite an old one, so that'll work just fine. Let's go over the pin wiring or the layout. I'm going to run down the left side here of the controller. First one is pull positive. That connects via this green jumper wire to a rail on my breadboard that has positive 5 volts coming from the Arduino. Second is pull minus. That is connected via this black jumper wire, and that comes over to pin 9 on the Arduino. Third is DIR, direction plus. Again, 5 volts via this green jumper. Direction minus is this red jumper wire, which goes to pin 8 on the Arduino. I am not using the enable positive or the enable negative pins. Moving down, DC ground is this blue connection here, which is connected over to the ground on my breadboard. The breadboard is also grounded via this green jumper wire in the top of your screen over to the ground on the power supply. And then the DC positive right here is the 24 volt signal, positive signal from the power supply. The final 4 connections on the stepper controller are your 2 pairs for your Nema 34 stepper motor. It seems like the common thing to do is folks use little tape flags to show direction, speed, and control. It does a good job. What it doesn't do, which I think is really cool, is show off the power of these motors. So for you guys that follow my videos, I primarily really run a machine shop, and I do more of the electronic stuff as a side to that. We've got a big 1/4 inch steel plate here that I had for another project. Let's hop over to the machine shop. We're going to drill out this hole and weld a coupling on it so that we can fasten it to our stepper motor. This weighs about 7 pounds as is, and we're going to add some weights to it and really show off the power of this guy. If you're not interested in the machining part, no worries. Jump forward to the time below you see in the video at the bottom of this screen to where we go over the stepper code and show the final results of this project. We're over on the Tormach PCNC mill now. We've got our plate bolted down to our fixture table. We've got a set of parallels underneath where the clamps are located that'll hold it off the fixture table so we can mill all the way through the hole without worrying about bottoming out. We're going to use a 4-flute 1/4 inch carbide end mill. We're going to come down and we're going to take a few width and depth passes to machine that out to a 3/4 inch hole, and then we'll hop over to the lathe and turn ourselves a little bushing that we can weld in there. And now it'll come in and take one full depth pass for a skim cut. 3 thou off the side. Perfect. Let's undo our clamps, take a look. Looks good. Let's just take a deburring tool. Break those edges. Okay, let's hop over to the lathe, turn our bushing. We've got a 1-inch piece of steel chucked up in the lathe. We're going to face off the front here first and then drill. Our drilling operation is going to be a center drill, then a 27/64, which is slightly under 1/2 inch, and then we'll ream to 1/2. Slow it down just a hair for this. Okay, that's drilled far enough so that we can get our reamer 1 inch deep, which is what we want for the through hole. We've got our 499 chucking reamer in here. We'll turn it down even slower to a few hundred RPMs. Okay, now let's break that edge. And while we're over here, let's break the outside edge. We'll just turn the lathe in reverse, and we'll come and kiss. Like so. Now what we're going to do is we're going to turn the outside just to get a true OD on the part, and then we're going to turn down our 3/4 inch bushing to weld into our plate. Okay. Let's see where our OD is now. And you can see we didn't actually even turn off that complete diameter here, but that's okay. So we're at about 7 under, so 993 or so. And we want to turn this down to about 750. So it's 121 on the dial. Take that in a few passes here. We'll go 50 to start. Another 50. Okay, let's see where that puts us. We're at 780, so we're going to take 15 more per side, and that should put us right on. Perfect. Let's clean up that OD a little more, and then we're actually going to turn this down. We only want a 1/4 inch sticking out, and we've got, about a 1/16 more. Break some of those edges real quick. Okay, let's part it off. We'll be done in the lathe. Let's test the fit. Perfect. Just a nice friction fit. You can twist it, but there's no real play in that hole. Looks good. Like so. Let's drill a set screw now. And let's tap it. Grab some cutting fluid real quick. Perfect. Let's go weld this together. Threw a 1/2 inch bolt through there and tightened it down. That'll do just fine to hold our bushing in place when we weld it. Shouldn't move much on us at all. I've got this set up on my plasma table. I don't have a good welding place right now. Got to figure that out. I just got the surface grinder in, so I am running out of room. This would be a great project too if you've got a rotating welding table that'll actually, turntable the part for you while you sit there in one position. So I'll have to move it around a few times. Won't end up being the prettiest weld, but it'll do just fine. Okay, we'll let that cool for a minute. I didn't weld right in front of the threaded hole just to make sure none of the weld splatter got in there, and we could always chase it out, but there's no need to. So we'll be back in a minute. While the weld is cooling, let's take a look at the Arduino code. This is very straightforward. I'm not going to post this online. You can retype it very quickly. The first program uses a potentiometer to control the speed. We've got that potentiometer on analog pin 3, and we set sensor value equal to pin 0. Pin mode 8 and 9 is outputs. These are the direction and step pins for the stepper. We write them low to begin with, and the program is quite simple. We read the potentiometer value, then we map it. That potentiometer is a standard analog input. In Arduino, that's 0 to 1023. We're going to map that to a range of 3600 to 1. And what that is that controls our delay. And we do this opposite because we want it to go faster. And by going faster, we reduce the delay. So we write pin 9 high, that's the step pin. We delay for the value of the potentiometer, and then we toggle it back down to low. That's how stepper motors work here. They alternate high-low in that pulsing. The other program is simply the cell stepper sketch. You can download this library. I did nothing to this code. I think it even has the same pins to begin with, and this does the ramp in and ramp out of the speed. And we'll show you here in a minute. I threw the stepper motor in a vise just to hold it down. Let's see how our plate fits. Perfect. No play at all. Throw our set screw in. Okay. Let's take a look. So the first program I've got is the potentiometer one, and you can see in the background I've got a little 10K potentiometer, and as I rotate it, it'll change the speed of the platter. Let's plug in the USB, power up the Arduino. Okay, I think that's the slowest setting I've got it on. And we'll speed it up gradually. Just like so. And then let's upload the other program, which is the smooth stepper, the cell stepper, which will just do a nice ramped acceleration and deceleration, and I think it changes the speed, the direction as well. Here we go. Yeah, there we go, backward and forward. Just like so. That's it for today, folks. If any of you have suggestions or comments, please post them below. If you're interested in seeing more of this and you don't subscribe, please do subscribe. Otherwise, take care. Thanks.